right, this is going on page 133 when we are done. So we're going to talk about limits at infinity. So limits at infinity are directly related to end behavior. And we first talked about end behavior in August. We've been talking about it a lot. We don't care about what's going on in the middle. It's way out at the ends, at the infinities. That's why these are limits at infinity. So end behavior of a function can be discussed in terms of limits at infinity. Recognizing the end behavior patterns of power, polynomial, and rational functions can help identify limits at infinity without graphing. So we're going to talk about power and polynomial functions first. So if we have a power function, that means it's like y equals 3x squared, not y equals 3x squared plus 2. That's not a power function, that's a polynomial. Okay, so just like literally one little term there. So if we remember, when n is even, and we're looking at the end behavior, we don't care about what's going on in the middle. If n is even, then the end behavior model is a quadratic, and it's up, right? So like 3x to the fourth, up. Negative 3x to the fourth would be down, right? Because it's a reflection. If it is odd, the end behavior models a cubic, down, up. If it is negative, then it would be up, down, right? Make sense? So we were writing this as, back in the day, as x approaches negative infinity, f of x approaches infinity, whatnot. We're still saying that, but we're saying it in limit notation. So we would say the limit as x approaches infinity of f of x, okay? You have to have the limit of what? It's the function, whatever it is. The limit as x approaches infinity of f of x is equal to infinity. And I'm going to talk about this a little bit more as we go. We can't really say that it equals infinity or that it's equals to does not exist, that type of thing, because infinity is not a number. We are going to write it like this on here. I'm afraid that if I put everything in this super correct infinity notation right now, I might lose some of you just as far as the concept is concerned. So I would rather teach the concept, use equals where you're used to them being, and just kind of tell you that's not really right. Because I feel like that's a really easy fix moving forward once you get the concept. You with me on that? So as long as you understand infinity is not really a number, we technically wouldn't be like equals that. I just want to, I always feel bad when I'm not doing it right because I don't want you to move forward and be confused. But all right, so then we write the limit as x approaches negative infinity of f of x would also equal infinity. So then we're just going to write the end behavior of the odd in limit notation. So the limit as x approaches infinity of f of x would equal what? Infinity. And the limit as x approaches negative infinity of f of x is equal to what? Negative infinity. Everybody okay with that? Just same in behavior stuff you've known forever, just rewriting it in limit notation like we've been doing this last week. Okay? All right, so then let's talk about polynomials. So with the polynomials, so the polynomial function, you know, just for a generic one looks real weird like this, but again, we're talking like 3x squared plus 2x plus 7 or whatever, has multiple terms. All we really care about is the leading term. So the limit of this entire polynomial, no matter what it is equal to the limit, so I'm rewriting the limit statement, as x approaches negative infinity. I'm just rewriting what was there. So the limit of the whole thing is equal to just the limit of the leading term, which would be, so like if it was 3x squared plus 2x plus 7, I would just care about 3x squared, then I treat it like my power ones. Okay. And then the limit as x approaches infinity, instead of the whole thing, just a sub n times x to the nth. And again, that's just like your official notation, what it would look like in a textbook. All it's saying is, so this means the end behavior of a polynomial can be described as the end behavior of its leading or highest degree term. So if it's not in order, if it's in order, it's your leading term. If it's not, it's just the one with the highest power, which would be the leading term if it was in the right order. Okay, we good with that? So we're going to rewrite some of these because we just need to make sure we can rewrite with our notation as well. And after I got through these 4 last periods, somebody was like, how are you deciding if you're using positive or negative infinity? Because I'm rewriting this part. Okay, I'm not making it up. I'm just rewriting what's there. It wasn't like I was just deciding off the top of my head. I didn't realize they were confused about that. So the limit of this is equal to the limit, and this one says as x approaches negative infinity, that's why I'm using it. So the limit of the entire thing is equal to the limit of just the leading term, which is x to the 4th. Well, that's even and it's positive, so my end behavior is up, up. So what's my answer? As the limit as x approaches negative infinity is infinity. So remember, we care about the end behavior. The middle can be doing all kinds of things we don't care about right now. So when I look at number 2, I have the limit as x approaches infinity. What's my leading term? Negative x cubed. So negative x cubed, right? So since it's odd, it reflects a cubic, which is down, up, but that's negatives, which means it's really up, down. So what's my answer? If I'm going to infinity, it is negative infinity. Same in behavior like when we were sketching stuff. Remember all that? Same concept, right? We're just kind of talking about it a little bit differently, but we're finding the same stuff, really. All right, on number 3, this is equal to the limit as x approaches negative infinity. What's my leading term? Then negative 8x to the 6th, right? So that's even, which means that the ends are the same. It's negative, so that means it's down, down. So what's my answer? Negative infinity. When I rewrite number 4, this is equal to the limit as x approaches infinity. What's my leading term? Negative 3x to the 7th. That's odd, so down, up, but it's negative, which makes it up, down. So my answer is negative infinity. Any questions about those, about where I got anything? Because if that kid hadn't asked that last period, I wouldn't understood why I was so confused. Everybody understand where I'm getting everything? Okay, good deal. All right, so let's talk about reciprocal functions. So our reciprocal functions are if I just have 1 over x or 1 over x to some other power, right? If it's just plain old 1 over x, then I have an asymptote at y equals 0. So my end behavior, the limit as x approaches negative infinity is 0. And as I approach infinity, it is 0. One's from the bottom and one's from the top, but I'm still approaching 0. Would we agree with that? Right, so then this is what it looks like, and it says where n is a positive integer. It does have to be a positive integer, but it has to be an even positive integer. I left off that word. Here is, turn that off. It's still approaching 0, right? This time just from the top on both of them. Now, one of the things that we skipped, because we skipped 9.3. 9.3 was a bunch of limit properties, and I feel like moving forward, if you do take calculus, you'll remember some of this basic limit stuff, because it's not that crazy hard, right? But all the rules and what you can do and all that stuff, it wasn't worth trying to get everybody to learn it right now. And we can still do what we needed to do with the basic stuff. So I'm telling you that because we're going to use some of the properties that we would actually talk about a little bit more in depth if we were moving a lot more forward with this. But if I have the limit of 2 terms, I can split this into the limit of this minus the limit of this, right? I can do that. That's one of the properties that's allowable. So that's something we're going to do right here. Just kind of telling you it's okay, and this is what we're going to do, okay? So if I have, so we know if it's just 1 over something, whether it's an even integer or this would be like 1 over, if I had x cubed, it would look like that. We just know that that's going to 0, right? So when we evaluate this, I'm dropping the limit statement. We're not rewriting it because I'm actually evaluating this, right? The limit as x approaches infinity of 1 over x to the 4th is 0 because I'm going to have an asymptote at 0, right? And then minus, well, the limit as x approaches infinity of 7 is just 7. So my answer here is -7. Okay. We good with that? Okay. Then the limit as x approaches -infinity of 5 over x squared is what? 0. And then 1 over x is what? 0. So my answer is 0. Now, there's some really weird stuff with infinities. Let's talk about a couple of them right now. Infinity is infinity. Infinity squared equals infinity. Infinity to the 5th power equals infinity, right? Now, negative infinity, if I square it, negative infinity squared is positive infinity because the sign is different, right? And then so negative infinity to the 3rd power is negative infinity. So you have to pay attention when you're dealing with negative infinities, and you are not necessarily if it's going to be 0, but in some other cases, you have to pay attention to the sign there, okay? And we'll look at that again when we get there. But what's infinity divided by 2? Infinity, right? Infinity times 2 is infinity, right? Infinity divided by infinity, not necessarily 1. Yeah, I know. Infinity can really make your brain hurt, but we'll talk about little things. Other things are going to have to come later because it can really get intense. All right, so let's look at rational functions. Technically, our reciprocal functions are rational functions, but these are rational functions where you have an x in the numerator and denominator, basically. All right, so if I'm given this, I can't just put in my infinities because look, I'd end up with like infinity over infinity here, and that's not going to help me any, right? So what we have to do is divide both the numerator and denominator by the highest power of x that appears in the denominator, okay? Because if I just substituted in negative infinity here, I'd get, what would I get? I'd get infinity over negative infinity, and that is not -1, okay? So here's how this works. We're going to take the highest power of x in the denominator, which is cubed, and we're rewriting this whole thing, so I have to rewrite my limit statement. The limit as x approaches negative infinity of, all right, so it's x cubed, so I'm going to get 6x squared over x cubed plus 2x over x cubed, and then in the denominator, 2x cubed over x cubed plus 3 over x cubed. So I literally just divided every term by x cubed because the highest exponent of x from the denominator was x cubed. Okay? Everybody with me so far? So now we're going to simplify this. So this is equal to, I still have my limit statement, the limit as x approaches negative infinity of, so that 6x squared over x cubed is going to give me 6 over x. Plus, this will be 2 over x squared. Then in the denominator, I get 2 plus 3 over x cubed. Okay. Everybody okay with where everything came from? It looks really yucky, but it's not that bad. We have made it into something that we can actually, our rules from the front that we can use. Where the polynomial rules didn't work because we got infinity over infinity. But here, now I'm going to evaluate it. Since I am evaluating the limit, I drop the limit statement. And I do each term separately. What's the limit of 6 over x as x approaches negative infinity? 0. Plus, what's this limit? 0, right? And in the denominator, this is 2 plus, what's the limit for that last term? 0. So I get 0 over 2, which is what? 0. If I'd have gotten 0 over 0, that's the indeterminate form. We still would have had to do something else, but we shouldn't get that if we do this correctly. Okay, we good so far? All right, so let's do that on number 10. This is the limit as x approaches infinity, and the highest exponent in the denominator is x squared. So this is going to give me 5x to the 4th over x squared over x squared, plus 2 over x squared. Then I simplify the limit as x approaches infinity of, so in the numerator, I'm left with 5x squared. In the denominator, I'm left with 1 plus 2 over x squared. So now that I have divided and I've simplified, I can evaluate, which means I'm dropping my limit statement. And we're going to do some slightly illegal things, but it's okay. Well, nobody's going to math jail. We're going to keep our mouth shut. Okay, so what is the limit as x approaches infinity of 5x squared? This would be up, right? So it's infinity. Okay. And then 1 is just 1 plus, what's this limit here? 0. So we really have infinity over 1, which is just infinity. So the illegal stuff here is you really don't substitute it in infinity because it's not a number, right? And these equal signs really shouldn't be here. But I'm afraid if we just kind of end up with infinity there and we don't write anything, it's not going to make sense if you go back and look at it. So as long as you know that's only semi-legal right now for it to make sense to us, when it really, really matters, it's going to be explained to you better and the notation will be there and it'll all be fine, okay? But I think it helps to kind of get this way. We good? Okay. Not a big fan of doing stuff wrong on purpose, but I do it wrong on accident all the time. But. All right, let's look at number 11. So this is equal to the limit as x approaches infinity of, so the highest exponent of x is just 1, so this gives me 2x over x minus 7 over x, and then 8x over x plus 1 over x. Then I'm going to simplify. So 2x over x is just 2 minus 7 over x. And this will be 8 plus 1 over x. So now I'm going to evaluate my limit. 2 is just 2. The limit of 7 over x as x approaches infinity is what? 0, right? Oh, and I don't know that we really talked about why that is. I probably should have a sort of skip that on the front. But if you think about, as x approaches infinity, that denominator gets bigger and bigger and bigger. And the bigger the denominator gets, the smaller the fraction gets. So if the denominator gets infinitesimally big, the fraction gets closer and closer to 0. That's what's happening there. Then in the denominator, this would be 8 plus 0. So that's 2 over 8, which is 1/4. What questions do you have at this point? Okay, so let's go back and look at these three together. These are rational functions. You first learn rationals in Algebra 2, and you talk about some rules. Then we talked about them again, and we talked about some of the same rules, and it had to do with the asymptotes. Okay, so if for rationals, we have vertical asymptotes, horizontal asymptotes, we have slant asymptotes, you can have all kinds of asymptotes, right? But the end behavior is always related to the horizontal asymptotes, right? That end behavior, what is it approaching, right? Maybe an asymptote stops it, maybe it doesn't, and it goes to infinity. Well, when we graphed these, one of the things we looked at was what were our horizontal asymptotes. And so we looked at whether it was top heavy, bottom heavy, or tied in degree. Remember that? So if we look at the two leading terms here, is this top heavy, bottom heavy, or tied in degree? Bottom heavy. Okay, so we're going to label this one bottom heavy. Right? Then we look at this one. What's that? Top heavy. And then what is this? Tied in degree. So if your function was bottom heavy, you have a horizontal asymptote at y equals what? 0. If it was top heavy, you don't have a horizontal asymptote, right? But it opened the door for a slant asymptote, but even a slant asymptote would still let it go to infinity. It's not going to affect the end behavior. So since we don't have a horizontal asymptote, that's why it would go to infinity or negative infinity. If it was tied in degree, then your asymptote was at y equals the ratio of the leading coefficients, which in this case is 1/4. Okay? So there's a reason that, and I know it drives you crazy, it did me too when I was in school, that math teachers take you through the hard way and then show you the easy way, okay? Because the hard way is where the math is and why it works and what you would have to do. So all this stuff that we just did, you need to understand that it's a process and how to do it. But guess what? If you know your rationals, you can just use your rational knowledge with your asymptotes, okay? It's that simple. So let's look at this. It says, looking at the examples above, notice that the limits of rational functions at infinity follow their horizontal asymptotes. So if I have f of x, so p of x over q of x, which means I have x's in the numerator and denominator. If the degree of p is less than the degree of q, that means that it is bottom heavy. We knew already that our asymptote was at y equals 0, which means the limit is 0, because that's where we're going, right? If the degree of p is greater than q, that makes it top heavy. And then that means your answer is plus or minus infinity. It could be positive or negative infinity. This one you have to think just a little bit more, but it's not that bad. Then if they're equal, that means that they are tied. And just like with the asymptote, the limit is the ratio of leading coefficients. So we have 3 more questions, just like the 3 above. But we don't have to do all that x dividing stuff because we can use what we know about rational functions. When we look at number 12, I look at my leading terms. Oh, not always the first 2, right? Should be if it's in the right form. But top heavy, bottom heavy, or tied in degree? Bottom heavy, so my answer is 0. Then I look at these. See, this is not the first 2, but it's the 2 leading ones. Top heavy, bottom heavy, or tied in degree? Tied in degree. So my answer is, try again, -5, because that's a -2. And then I want you to change number 14. It says as it approaches infinity, but I want it to be oh my goodness. I want it to be negative infinity. Why does this board hate me? So make it the limit as x approaches negative infinity. All right, so let's think about what is happening here. Here, it is top heavy, okay? So my answer is either positive or negative infinity, right? And you have to pay attention to your signs. So my suggestion is that we don't really input the infinities, but maybe just the signs of what's happening. So we have this negative out front, right? Then in the numerator, negative infinity cubed is going to be what? Negative infinity, that's a negative. And then in the denominator, negative infinity squared is going to be what? Positive infinity, right? Or it's going to be positive, that's all we care about. So we have basically a negative times a negative, which means my answer is positive infinity. Okay? So pay attention to those signs on those, because that can get tricky. If it's positive infinity, you don't really have to pay that much attention, because it's just all going to stay positive. But watch out for the rest, okay? What questions do you have? Anything? We good?